Yeah. Okay, welcome back, everyone. I think we've got a very different day in school today. Scott Morrison from ANU is going to be talking what the title on the board.
Thank you. Okay, so today I'm definitely talking about an application of category theory. The problem that is going to motivate the whole day's talks are understanding subfactors, and in particular trying to understand small index subfactors. I'm going to presume that nearly everyone in the audience knows almost nothing about subfactors, so we're going to start right at the beginning of what those are, and then describe how we turn it into a problem in category theory, and then spend the rest of the day doing some very applied category theory back on this problem. So just a few things to get started. We recently finished writing a survey article on this whole problem with Vaughan Jones and Noah Snyder, and that's the number on the archive, and it actually pretty closely follows what I'm going to say today. So if you want to read along or look back later, you can check there. Also, my notes for my talk today are online as well at that URL. Those notes are actually a very strict superset of what I'm actually going to say today because I wrote too much. And that said, since there's no way that I'm ever actually going to finish the notes I have written here, you should interrupt as much as you like and derail me as often as you like, because we're not going to get to the end anyway. We might as well have fun along the way. Okay. So before I actually tell you what a subfactor is, I just want to make some sort of very general remarks about how you should think about today's problem as a category theorist. So this is obviously simplifying things a little bit, but I think you could maybe say that there are two reasons to use category theory in mathematics. And one of them is sort of following what Grothendieck showed us, that sometimes it's just great to study objects from the outside and study maps between them rather than the gory details inside. And often this leads you to really powerful perspectives that make everything easy after the fact. But a completely different reason is just that sometimes category theory, or the language of category theory, gives you very convenient ways to axiomatize particular algebraic or topological objects. And I think really everything that I'm going to say today fits very well. Maybe sort of just to give you an example of what I have in mind by that very concretely. I think Richard mentioned this yesterday. He only mentioned harder versions, but you can think of a group as a category with one object where every morphism is invertible. I mean, that's not the most convenient way to say what a group is, but if you already knew category theory, maybe that's a decent way to do it. So that's what I have in mind as sort of the second sort of thing.
So would it be reasonable to characterize that as a small-large distinction?
Yeah, sure. Yeah. We're definitely on the very small side of things today. Okay, so we definitely fall on that small side, and so let me write something to get us started. So we'll study subfactors, which I'll come back to, via this gadget called standard invariant. It's not a very descriptive name, but I can say right away what it is using some category theoretic language, which is, so it's a unitary pivotal two-category. So again, I'm going to come back and make sure that everyone knows what unitary and pivotal mean, but happily everyone here is very happy with two-category. I'm going to say a little bit more. With just two objects. So this is not quite a monoidal category, but it's pretty close. Call C and D for now. And a generating one morphism between those two objects. So somehow everything in the category is every one morphism is going to be a summand of some composition of this one morphism with its dual. Okay. So we can make all these adjectives in here and so on precise, and obviously this is an example of specifying some algebraic gadget by just using convenient language from category. Okay. So if that's all I'm doing, why on earth am I here? If a geometric group theorist turned up here and prefaced their talk about geometric group theory by saying, recall that a group is a category with one object and all morphisms invertible, and then continue talking about geometric group theory, you'd rightfully be quite annoyed, I think. And so the way I've presented things so far, maybe you're annoyed already. But there is something going on that I think is interesting to you guys, which is that this thing that we're going to try and study, this is this is genuinely higher categorical. Now it's not very high. It's only n equals 2. But it's high enough. And what I mean by that is that in order to understand this gadget, we're really going to have to pervasively use two-dimensional topology in analyzing these objects. And I think that in studying this problem, the subfactor and planar algebra communities have come up with a lot of really awesome tools that are really kind of specialized to this setting with all of these particular adjectives and constraints. But I think the exciting reason to talk to all you guys as category theorists is that a lot of those tools we've developed for this specific setting should generalize a long way, some of them all the way up to when you just have the word 2 category. And you guys should pay attention and see if you can think about ways that the things that I use today can be thought of more generally. Okay. So, what's the actual problem we're going to study? So there's a measure of size. Of a subfactor. I promise I will still come back and say what a subfactor is, which in this language is the dimension of this object x all squared. In a pivotal setting, we have notions of dimensions called the index. Now, classifying all subfactors, whatever they are, is a completely hopeless problem. And so we make life easier for ourselves by just filtering by the index and trying to understand subfactors with small index. And the basic history here is that for index most 4, everything is well understood since the 90s, mid-90s. But then on the other hand, for index above 6, or I guess 6 as well, there are certain sort of wildness phenomena, which, well, it's possible to say some things, but there's a transition at 6 and life gets distinctly hard. And so if you already cared about subfactors, which obviously not many people in the room do, you would you have an obvious problem here to understand everything inside this gap. And so we now know what happens all the way up to 5. So we've done half of the problem. We're still working on the other half of the problem. It's definitely going to be harder than the first half. But this survey paper tells you everything that tells you the complete story for index less than or equal to 5. Okay. And there were 2 giant surprises.
I presume.
Yep.
I presume from these inequalities that this is a kind of dimension which could be not an integer.
Absolutely. Yes. Yes. Sorry. I guess in a category theory audience, I guess presumed that of course dimensions aren't integers. What a strange idea. Okay. Yes. Very much all the interesting stuff is happening at the one of the reasons why things become wild is because 6 is an integer with an interesting factorization, but most of the surprises that I'm talking about here are happening in the non-integer intervals between 4 and 5 and 5 and 6. Okay, 2 surprises. There are just these sporadic examples that come up when you try and do this classification problem. I'm not claiming that our classification problem is as nice as the classification of finite-dimensional semi-simple V algebras, but it sort of has the feeling of G2 popping out as you do a classification problem. There are just these things that we never would have noticed until we did this classification. So these, I think, some of these examples are fantastic, interesting objects we also understand them very poorly. We barely showed that they exist by sort of sometimes very unenlightened constructions. So there's a lot to be understood there. And the other big surprise is just the sparseness of the classification. Before we went into this, I think everyone expected that there was going to be lots of things here, and maybe the difficulty was that there were going to be too many things to get your hands on, and it turned out the answer is that there's basically nothing in this interval between 4 and 6. Even though we don't know what goes on up to 6, we have a very good sense now, and there are far fewer examples of these things than we deserve. So. Okay, so let's actually get started then, and I'll tell you what a subfactor. What a subfactor is. Let's see. So a factor, first of all, is a polynomial algebra with trivial center. One thing to say about, I guess, the next 5 or 10 minutes is that you should consider this general education. You don't actually need to remember anything that goes on this board to understand the subsequent 3 hours. But if you want to know what the words mean, you should read this. I won't say what a polynomial algebra is unless someone asks me.
What is it for
Okay, good. There are lots of different characterizations of what polynomial algebras are. I think the nicest one from our point of view is that it's some collection of linear transformations of a Hilbert space, some operator of algebras on a Hilbert space, which is equal to its double commutant. That is, everything that commutes with everything that algebra commutes with is the same thing as the algebra you started with. There are other more analytic ways of saying it, but that's a very algebraic way of saying it. And I think it's a good one because it sort of emphasizes that, that thing that I just said is certainly true of, say, matrix algebras acting on finite dimensional vector spaces. They're equal to, acting on sort of the right representation. And that sort of version of what polynomial algebras is sort of a clue that they're more like finite dimensional things than you might expect given their infinite dimensional algebras of operators on Hilbert spaces. Okay. And then there's a classification of factors into different types. So a factor is type 1, also known as boring, if it has minimal projections. So you know what a projection is probably. P squared equals P. You can think about what it means for one projection to be smaller than another just by the usual rules in finite dimensional linear algebra. And if you've got a projection that's got nothing smaller than it, you're type 1. And these factors are just the finite dimensional examples of n by n matrix algebras, and then all bounded operators on a Hilbert space. So they're not very exciting.
Why is it called a factor?
There's sort of an integral decomposition of von Neumann algebra. So given any von Neumann algebra, there's some measure space, so that sitting over each point in the measure space, there's a factor, and the whole thing is an integral of these pieces. And they should be called. You're integrating them, not multiplying them. That's sort of the wrong word. But, yeah. Okay. So a factor is type 2 if it has no minimal projections. So we're in a weird setting already, far from the finite dimensional case. Every projection you find has something a little bit smaller sitting underneath it. But there is a trace. That is some map from, I guess I haven't given things names, to sort of an extended value trace. The trace of some things might be infinity, but trace of AB is trace of BA. Now, there's sort of a further subdivision here. If that trace can be normalized so that the trace of the identity is 1, in particular that just means it's not infinity, we say type 2 subscript 1, and otherwise identity. And then there's sort of the basket case of everything else. Say it's type 3. And these are important and interesting objects, but not today. We're always going to be interested in this type 2-1 case, but I'll sort of omit saying type 2-1 probably anytime I mention factors. Okay, so let me give you an example of such a thing. So the prototypical example of a 2-1 factor is the hyperfinite 2-1 factor. So hyperfinite means the same thing as, well, approximately finite dimensional. If you knew about C-star algebras, it's sort of a limit of finite dimensional things. And here's one way to write it down. Just take the limit of increasingly many powers of 2 by 2 matrices. So you can see how to include up, if I take 2 to the n by 2 to the n matrices, I can include that up into 2 to the n plus 1 by 2 to the n plus 1 matrices by tensoring with the identity 2 by 2 matrix. And so this gives me this long list of algebras sitting inside of each other. And you can take the limit, you can construct a trace on this thing just by taking the obvious normalized traces on each piece, and you get this thing. And it turns out it really is the hyperfinite 2-1 factor. There's only one 2-1 factor that you can construct in this way, sort of coming from a limit of finite dimensional things. What's that?
Is it just the topology?
Yes. So, factors, well, 2-1 factors at least, or hyperfinite 2-1 factors at least, aren't very interesting. There's just one of them. Not much to study. Okay. But then a subfactor is an interesting thing. The way that a 1-2-1 factor sits inside another is extremely interesting. The subfactor is an inclusion of factors. A sitting inside B. And sort of, you should be thinking that we're going to try and do a kind of Galois here, understanding how one factor can sit inside another. Oh. Let me say there's the notion of index sort of analytically, without actually defining all the details, but we can say how big B is relative to A. Well, let me just say this quickly, but using this trace, you can complete these things into Hilbert spaces. This big algebra has a this big algebra is a modulo of the small algebra, just by multiplication. And there's a notion of dimensions of L2 representations of one-dimensional algebras, which in particular is some real number. Okay. I mean, I'm not going to define this theory of dimension because we'll have a categorical way of thinking about it in just a moment. Okay. You can now forget any mention of analytical issues or so on. We're going to turn to category theory now. Okay, so what do? Well, given this subfactor A inside B, and anytime I write A inside B from now on, I mean an inclusion of 2-1 factors. We can analyze the bimodules. And they come in 4 flavors. That is, we can look at bimodules for the algebra A acting on both sides, or we can think about bimodules with A acting on one side and B on the other, and so on. Now, we can tensor bimodules together. And whenever I tensor bimodules, I mean tensoring over the ring that sits between them. So, e.g., well, we have sort of some basic bimodules that we're sort of guaranteed to have just from an inclusion. We can think of A itself as an AA bimodule, and then we can also think of B as a bimodule in a few different ways. guess there's no reason for me to not write B as an AA bimodule. Okay. So there are these obvious things that you get for free as soon as you have an inclusion. This notation just means I'm thinking of B as a left B module and a right B module. But then we also have things like, well, we could take B as an AB bimodule and tensor it over B with A. Okay? Turns out that one is just B as an AA bimodule because you can move elements of B back and forth between these two tensor factors just belong together. Do that. Or you can do slightly more interesting things. You could think about so you can think about B as an A module and end up with some interesting BB bimodule here that wasn't necessarily on this previous list of things. Okay? Now, there are sort of two versions of this story. We can either think about bimodules that are themselves Hilbert spaces, and then we have to use a fancy version of tensor product due to Kohn, or we can just ignore that happily, it turns out, and we can just do this entirely algebraically. These bimodules are just vector spaces with algebras acting on them. And this tensor product here is just the usual sense of tensor product over a ring. A happy result says that there's an equivalence of categories between the algebraic and alternative worlds. Okay. So the final thing to say about bimodules here is that we only consider some bimodules. If you wanted to know all of the BB bimodules for some factor B, there'd just be some ridiculous list. We only consider the bimodules tensor generated. That means appearing in some ands of the following tensor products. We take B as an AB bimodule and B as a BA bimodule. And you're just going to worry about the bimodules that you can find by decomposing tensor products of these guys with each other some number of times. Okay? So that's some collection of bimodules. So what is this thing that we're looking at now? We should try and axiomatize this equation of this collection of 4 different types of bimodules. And so the theorem is that this gives us a 2-category. That was convenient. I didn't find that at all. I just need to write theorem on top of that. Okay. Okay. So, now, the proof of this theorem definitely involves a bunch of analysis, and you really have to go away and think about von Neumann algebras. But once we're done with the proof, which of course we're not going to do today, then you're home free and in category 3 land. So the theorem is just that the collection of all these bimodules form a unitary, pivotal 2-category with 2 objects. Maybe it's silly to call them C and D now. We should have just called them A and B all along. So the objects you think of as the pair of algebras that you're looking at, and the generating one morphism here, well, we're thinking of B as an AB bimodule. We're thinking of that as a morphism from the object A to the object B. And now I've said 2-category here, but all the way on the previous board I was talking about tensor products, but tensor product is just the composition of one morphisms. And in fact, I sort of don't understand why category theorists don't just do this all the time. You should just use the tensor product symbol for composition of one morphisms in a 2-category and be done with it. It's sort of, I feel like it would make the whole subject less intimidating to realize it's just like tensor products, except sometimes you can't take tensor products if the object is. Anyway, end of rant. Okay, so here's the wonderful, wonderful theorem. So let's, before sort of talking about what goes into the proof, let me just make sure that we know what we're talking about. Okay, 2-category, fine. Let's say what unitary is. Now, what's that? No, we can work as strictly as we like. The 2 categories are strict. The pivotal structure is a strict one. One of the joys of being an applied category theorist is that you have no obligation to work in the maximum generality. You can just work with the examples at hand. And so, yeah. your mission, should you choose to accept it, is to see how much of this you can drop and weaken and still prove theorems.
But you would have to strictify the tensor product in order to get a tensor.
Yeah, but it's sort of, I mean, it's no worse than strictifying tensor products of vector spaces or something. It's still, yeah, sorry, you're we can meet you. Okay, so what is unitary? Well, unitary means there's an anti-linear map. So suddenly, without warning you, I'm working over the complex numbers. So these are, to me, it's so obvious I didn't even say it. These two categories are enriched in complex vector spaces. The two morphisms live in complex vector spaces. So you know what anti-linear means. And what this is, so we usually write this bar, so it's sort of like complex conjugation. Well, it's actually like adjoint in Hilbert spaces, but star is already used in category theory, so we have to use a different bar. Okay, so all that it does is it takes a two-morphism between one morphisms x and y and gives you a two-morphism pointing the other way, between y and x. Okay? Such that, well, as soon as you have this bar, you can define an inner product on each of these spaces, two morphisms from x to y, by taking the trace. I guess I should have said this in the other order. I'm not really allowed to use trace until I've explained pivotal, but trace is something that the pivotal structure gives us. And this in particular is just a number.
So there's an operation on one morphism as well. It's implied by this operation on two morphisms.
No. This is like extending a sort of an SO2 action to an O2 action. It's adding. You should think of it as reflections on two morphisms. But it's.
So what are x and y?
X and y are one morphisms with the same source and target zero objects. Yeah, sorry. These are. I didn't give my category a name. These guys can see. Okay. Well, I realize I've missed one thing here that I should just tack on to the theorem. That the identity on A is simple. So I just mean that endomorphisms of the identity on A and similarly B is just the complex numbers. Okay? And so this trace here, I'll say what a trace is in a moment, this is just some complex number. Okay? So we really are defining an honest inner product there. And saying that this category is unitary is saying that this inner product is a positive definite inner product. Now this is already a gigantic assumption. But it's sort of justified by the examples we have at hand. And moreover, it turns out this is something we do understand you can weaken in quite considerable ways. And you can prove classification theorems largely dropping the word unitary. But I'm going to avoid that to make life easier. Okay, so there's this bit of structure. And maybe I should say that having this positive definite inner product on the two morphism spaces ensures that our category is semi-simple. All of the home categories are semi-simple categories. But I think that we can largely, we don't really need to think about that too much. Okay, so what's pivotal? It should have come first. So pivotal essentially means you can draw nice planar pictures. So how does this go? There's a tensor product reversing functor from C to C called star with star equals 1 on the nose. So I'm really doing strict pivotal here. And also these evaluation, co-evaluation maps.
So tensor product mean composition of one cells.
Yes, tensor product always means the horizontal composition of one cells, as it should.
So another way to say that would be C off to C.
But I mean, by the time you're up at pivotal through categories, there are so many different things that opt could mean that it seems worth spelling out. Okay. Okay. These maps, which I'm just going to draw as little cups and caps. Now here, I guess I should draw an arrow on this here. And so for every one morphism X, I want to have maps like this. So here, of course, X is a one morphism, so it has sources and targets, which are either A or B. And so really, I should be drawing in this picture some region labels, which are either A or B. And some later, we'll keep track of those, but mostly we'll be lazy. Now, so there's this huge collection of maps for every X. There's a collection of maps like this, so that these all fit together in the nice way that Richard described yesterday. You can straighten kinks, and this duality functor on the level of two morphisms. So here's a two morphism. I'm going to read all my pictures from bottom to top, unlike Richard. So what does this mean? Well, we go up here. Sorry, I should use a different letter, because X is a two morphism. So X is a one morphism. This is a two morphism here. So I go up here and I use a co-evaluation map to create this pair of objects here, and I apply F to one of them, and then I kill off two of them again. Okay. This is just the same thing as the dual of that two morphism. Okay. So, no. This is star. Yeah. This board can't use bar because unitary and pivotal are orthogonal concerns. This is star is for rotating by pi, and bar is by reflecting. Okay.
If star is a functor,
Yeah.
what does it do to the objects?
Sorry. What does it do to the objects? Sorry, yeah, and it just fixes anything.
But then I can't.
Yeah. Am I saying something silly? Yeah, maybe. Sorry. Yeah. Yeah. Okay. It's. Yeah. I mean,
X goes from A to B, then X star has to go from B to A.
yeah. Oh, but doesn't this tensor reversing take care of that all by itself? Or I think that.
So if it's a functor from C off to C, it's supposed to take each object to an object.
Yeah. So we should take each object to itself. It would be ridiculous to do anything else. I think it's okay. So what's the point of pivotal? I mean, this is a silly set of axioms which I think confuses things more than illuminates things. The point is just that as soon as you're in a pivotal world, there's a system of sort of natural isomorphisms taking you from home x to y tensor z with home, how does this go? X tensor z dual to y. And what is this? Well, you can take something here that starts at x and sends you to y at z, and you send that to just this guy where you pull down z to the bottom using one of these evaluation maps. And really what you should be thinking in a pivotal category is that these distinctions, whether you've put tensor factors in the source or the target of a home space, is an artificial distinction, which we really want to get rid of. This notion of planar algebra that we're going to get to in just a moment is going to explicitly remove that artificial distinction and make us happier. because we're actually describing the right object now instead of introducing artificial extra copies of the things we're actually interested in. Okay, so what to say about the theorem? Let me maybe not write this down, but just annotate a little bit here. So these evaluation and co-evaluation maps here come from the theory of King's-Popper bases. You have to go and learn lots about von Neumann algebras, but it turns out that there really are those maps between bimodules, between von Neumann algebras, and they satisfy this property easily. This is hard, and sort of held up the subject for a while before people realized that that was something you could really prove about bimodules between von Neumann algebras. And the way to think about, what they actually proved here, star star is the full 2-pi rotation. So the full 2-pi rotation is defined in terms of these maps coming from King's-Popper bases, and then there's something to prove about those maps coming from King's-Popper bases. Eventually everything then fell into place, and we eventually got to sort of this way of saying what the standard invariant is. Okay, I guess one or two more things to say about this setting, which is that you can just look at the tensor categories you get looking at the endomorphisms of A and the endomorphisms of B. And those deserve names because we'll talk about them a lot. We call them the even parts of the standard invariant. So they're just a pair of tensor categories, endomorphisms of A, endomorphisms of B. And in a great many examples, and all of the most interesting ones, it turns out that those tensor categories have finitely many simple objects. So they're in some sense very small, very, very small things. And in particular, having finitely many simple objects and being unitary, so in particular semi-simple, they're fusion categories. So let's just quickly write that. Even parts and A and B are tensor categories, and very often fusion categories. So that's the relationship with fusion categories. We're not going to really use the theory of fusion categories a whole lot in these talks. I'm not going to go into a great detail about fusion categories, but it's worth being aware of. In fact, you can go very far talking about fusion categories, and it turns out one of these standard invariants is really exactly the same thing, well, subject to this finitely many simple objects business. The standard invariant is really the same thing as a pair of fusion categories along with a categorified Morrison equivalence between them. And you can read about all of that in papers at Muga. And so really, if you cared about fusion categories, this business is a very natural thing to do. It's studying Morrison equivalences between fusion categories. But that, for us, is just an aside. Okay. Let's start seeing how we understand the standard invariant. One thing that I should have said back in talking about pivotal categories, so let me just say that here, the dimension of an object X in a pivotal category is just the circle labeled by X, built out of evaluation and co-evaluation maps. An easy theorem, an easy sort of thing coming out of the proof of this theorem is that the dimension of X, all squared, is that analytically defined index of the subfactor that I mentioned before. But from now on, the index just means the square of that circle. Okay.
So,
Yep.
I'm a bit confused about the circle because
Yep.
you need to move like one goes from X star and X.
Yep.
One.
So we have, it's a good point. We have more evaluation and co-evaluation maps than I had first let on. when I
Oh, because the double dual.
because the double dual is the identity, you can draw these came in a particular orientation, but using the double dual, you
So
can
you
build
use
them going the other way.
one for.
Yeah, I mean, in the non-strict case, you'd have to have a copy of the pivotal natural transformation in that picture in order to make it make sense. Is that okay, or should I say that in detail? Okay. Okay, so we're now going to study this thing called the principal graph of a standard invariant, because we're going to need some sort of combinatorial invariance of these objects we're studying. So this is a graph, nearly always called gamma, and it has as vertices the simple bimodules. So that just means the simple one morphisms in that 2 category. So there are 4 classes of vertices in this graph, corresponding to AA, AB, BA, BB. And then there are edges between P. So P here is some vertex, a bimodule. And let's say that we're looking at a bimodule which is a right A object, that is the target of that one morphism is A, and Q, a right B object. So the number of edges between those 2 vertices is the dimension of hom. So we can take P, and it's a right A object, so we can compose it with B, okay? And so here we get, 2Q, okay? So these are, P and Q here have to have the same source, so let's just write C on the left, where C is either A or B, doesn't matter. And so we can think of homs as CB objects between P tensor B and Q. Okay, and that's just some vector space, and we can count its dimension, and we draw on this graph that many edges connecting those vertices. Okay. So there's a little bit of extra data we're going to decorate this graph with. We also record this duality functor, which is just some involution on the simple bimodules. It takes each simple bimodule to some other one, and it reverses them. So it's an involution fixing the AA vertices and fixing the BB vertices, and it's a bijection between the AB vertices and the BA vertices. Okay, so this is some extra combinatorial data that we're going to keep along with this graph. Okay, so this graph has 2 components. The left A and left B objects, just because the edges we described only connected things with the same source, so there are obviously 2 components. And just as a let me draw an example of a principal graph and then tell you a little bit more about our convention for drawing them. So here are 2 components. I'm going to draw a boring example where the 2 components are actually the same. So our convention is that the trivial bimodule for A and B is always the leftmost vertex when we draw these graphs. And then the second vertex is always going to be B. So B as a left A, right B object, and here's B as a left B, right A object. And then we draw the graphs. Notice that because there's this special vertex in the graph 1, you can always ask how far is some vertex from 1, which is also just asking what's the smallest tensor product of B and B dual that object first appears in. You think about what that means. And we're always going to draw our graphs sort of graded by that distance. So in some column, you have vertices that are a certain distance from one in this graph. And how are we going to record this extra data of duals? So we'll draw that little red lines. So remember that dual is an involution of, oh, sorry, that was the wrong places. Dual is an involution of the AA objects. So the AA objects are the things at even depth on this graph. Okay, that's an AA object. That's an AA object. These are both AA objects. And so those red lines means dual is interchanging those two, and these little red ticks means that those are fixed under duals. Those objects that are in duals. Similarly for the BB objects, we use the little red pictures, red lines. And then the final bit of the convention is that there's this involution. So there's this bijection between the AB bimodules and the BA bimodules, given by taking dual. And we won't ever draw this in pictures, but we always just mean match up the vertices at each depth in the order they appear. Okay, so the order in which the vertices appear at a given depth here is implicitly telling you how to take duals and which object you get up on the first graph when you take its dual. Okay, so we don't do all these. Okay, later, much later in the talk, we're going to end up drawing lots and lots and lots of principal graphs, and so I needed to explain now what they are. Okay, some things to say about the principal graph. The index is at least the square of the norm of this graph. So norm here means the norm of the adjacency matrix. And this is one last time where a little bit of analysis is required to prove that statement, so of course I won't do it. And then if the graphs are finite, that is, there's only a finite list of simple bimodules in this thing, the index equals the square of the norm of the graph. There's a few things. So this fact doesn't require any analysis, but does require you go learn something about Frobenius-Perron theory of eigenvalues of graphs, but it's something that you can do. The basic idea is just that, so the idea here is that the map, well, there's a function on these graphs. You can take some bimodule and send it to its categorical dimension, just the trace of that object in this 2 category, and that's some number. And in the unitary world, these numbers are all real numbers, not arbitrary complex numbers. And this function here on the graph actually gives you an eigenvalue for the adjacency matrix. And that lets you start doing this sort of analysis of relating the dimension functions with the properties of the adjacency matrix. Okay, but this is just the important result to remember. This is something that's not true if you drop the word unitary on everything. But if you drop the word unitary, then you see that these are Galois conjugates of each other rather than actually being equal, and you can pretty much do everything the same way. Okay. So we've extracted some combinatorial invariant from our setting, and we know how to interpret this number, the index. Okay.
These graphs are these trees.
No, definitely not. They get big and complicated. Okay, how are we going? Okay, so let me give a very quick example of this sort of setting. The amazing fact about the hyperfinite 2-1 factor is that you can realize any finite group, actually much more generally, any amenable group, as acting on it by outer order morphisms. And an even one more ridiculous fact is that at least for finite groups, any given finite group acts in an essentially unique way on the hyperfinite 2-1 factor. These are hard things to prove, but they're kind of cool. And so, in particular, we can build some examples of subfactors, and then I'll draw some examples of their principal graphs. So we have subfactors. So R, remember, was our favorite 2-1 factor, the hyperfinite one. And we can realize any group acting on it by automorphisms, and so we can take the fixed points. So we've got some finite group, it acts on it in essentially just one way, and we take the fixed points, and that's some subalgebra. And so there's a subfactor. If you think about it a little while, its index is just the size of the group G, so it's not a very exciting one. The dimensions are integers, and you can analyze everything here. So the RG bimodules. Remember that's some tensor category. Well, we're only looking at the ones, remember, generated by R as a bimodule over the small algebra. This tensor category turns out is just the representation theory of G. What else could it be? And the sort of the other category are our bimodules. What's this guy generated by? We're only looking at the things generated by what you get by looking at R tensored over the fixed points with another copy of R. Okay, those are all the things that we're going to be thinking about there. Not all bimodules, but just those ones. What's this category? Well, what other tensor category do you know that you can build only starting with a finite group? Just G-graded vector spaces. Okay, and you can draw the principal graphs. The principal graphs are just little spoke graphs, where here these are the vertices at depth 1 and 2 are representations of G, and the number of edges connecting things here is the dimension of that representation. And then the graph on the other side, which is coming from vec G, just has even vertices corresponding with elements of the group. And all the edges are okay. So if I had a bit more time, we could do that in detail. And it's something that you can do in detail yourself with basically just what I've told you. Let's just do another example of a principal graph to see that interesting things happen. Let's say we look at fixed points under H sitting inside fixed points under G for, better do it the other way. Fixed points under G sitting inside fixed points under H. H is some subgroup of G. Okay, fixed points get smaller as the group gets bigger. And it turns out here that the RG bimodules are representations of the big group. RH bimodules are representations of the small group. If you remember that these sorts of things, these are the even depth vertices on one graph, and these are the odd depth vertices on the same graph. But I'm not telling you yet anything about the RH bimodules or the RH-G bimodules. And it turns out those are actually a bit harder to say exactly what they are. These functors, if I take some RG bimodule and tensor it over RG with a copy of RH, okay? Now on the right, it's an RH bimodule instead of an RG bimodule, so we're in here. So we're meant to get some representation of H. Okay? And similarly, there's this other functor. If you start with rep H, here an RG RH bimodule, tensor it over RH with a copy of RG. Well, now you get an RG RG bimodule, so you must be here in rep G. Well, induction and restriction. What else could they possibly be? And so you can describe the principal graph very explicitly here. Maybe let me just sort of take a tiny bit more space. We could just look at symmetric group 1, 4 elements sitting inside the symmetric group 1, 5 elements. You get, well, what are so the even depth bimodules are representations of the big group, and those representations of S5 are just indexed by Young diagrams with 5 boxes. And in fact, there's a really easy combinatorial rule. If you take an irreducible representation of S5 and want to restrict it down to S4, you just have to look at all the ways of deleting one box from that Young diagram. So we know, if we believe that description, that the only guy this representation of S5 is connected to is this representation of S4. And now when you induct back up to S5, the rule is just think of all the different ways to add one box to the diagram. So we get that guy, and then you keep going. The only way to delete boxes here are that bottom box or that right-hand box, getting you to there or there. Then more interesting things start happening. Oops. Sorry. I think we're about to produce a little cycle like Mike was asking about a moment ago. Okay. Something's not quite right there. Oh, I missed one in between these two. That only has 4 boxes. Then it goes a little bit further. Here's the guy with 5 boxes. Okay. So anyway, these principal graphs record some strange analog of things like induction and restriction between a pair of representation categories, but in some more general setting. Okay, principal graphs. Let's ignore them for a little while. We'll come back to them lots and lots later. And in the last 0 minutes before we have a break, let me tell you the definition of a planar algebra. We could just have the break now and push that into the post-short break thing. I don't have a strong opinion. Should I spend 10 more minutes saying what a planar algebra is, or have the break right now and spend 10 minutes later? Break right now? Okay.